Okay, my wonderful physics students. Guys, I apologize that I am not at school today. We have a bit of a family emergency. I was planning on being there today. And so I want to get some notes done with you guys today. And then I think we'll have time to watch a little thing afterwards with the sub. But here's what I need you to know. I really, really need you watching, following along, and filling out your notes. Today, we need to take notes on projectile motion. And once we have these notes filled out and I see you guys on Tuesday, then we're going to dive into another project. It's a project I'm really excited about. You guys did so good with the egg drop. That was a lot of fun, and you guys really did so well with that. For this new project, we're going to be using these spring load cannons. Like, I have these little cannonballs, and like we load the cannonball and you like fire it off at different angles, and I have this really fun project planned for us, but you need to understand the physics behind it, and so I really need you to follow along and get these notes down so that on Tuesday we can jump right into that project. Okay, so we need to, learning target 2, draw force and velocity free body diagrams for an object on a projectile path. We need to be able to describe the acceleration of a projectile in the X and Y direction. So know I'm going to be breaking this apart. And then we need to know about launch angles of a projectile. I have very purposely left this vague because this is going to be your project where you're going to be experimenting and figuring out something about launch angles. So please turn to page 7. So on page 7, and guys, if you don't have your packet with you, will you please grab one off of the back table so you can follow along with us? So on page 7, what is projectile motion? So let me give you an idea. If someone fires off a gun, that bullet is a projectile. You've probably heard that before. But guess what else? If someone kicks a football, that football is a projectile. And so we have in physics this definition of what a projectile is, or something traveling under projectile motion. And here's the first important idea. This item is like traveling through the air. Traveling through the air. Okay, now here's a difference though. Yes, it's traveling through the air, but it's not an airplane or it's not a helicopter. It does not have any kind of like source of propulsion. So it's traveling through the air but not being propelled. Let's do that. But not being propelled, okay? So it's traveling through the air, but it's not being propelled, aka there's no engine, no fuel, no power source, okay? So it's just flying through the air, right? So something that is a projectile is traveling through the air. There's nothing that's propelling it forward. Sure, a cannon or a gun or a football player's foot could have started that motion. It could have supplied a force to get that motion going, but as the item is traveling through the air, there's really only one, maybe two forces acting on it. And so let's talk about that for a second. Let's say that we took out on the range, we take our gun, and we're going to fire a bullet from our gun. And we're not even going to put it at a launch angle, like perfectly horizontal with the ground. And here, like, what the path that we would see from the bullet over a much further stretch would be something like that, okay? Like, we got this path of our bullet here, okay? But let's think about the bullet at each moment along this path, really quick. So sure, I have the bullet was here and here and here and here, right? But what forces are acting on this bullet for each of those time frames? And I'm not talking about the moment of ignition. I'm not talking about when it was currently being fired. Because, yeah, right in this moment that the bullet is being fired, there's absolutely some kind of like propulsion or applied force. But after that, that is no longer true. Like, let's think about our football player right here, and we've kicked the football, okay? So what forces, after our foot is no longer in contact with the football, this is going to be a free body diagram, specifically forces, not a free body diagram for velocity. That will be here in a little bit. So let's draw a free body diagram for the forces acting on this football. Well, the football has mass, so we have a force due to gravity. Which is going straight down to the ground. We do not have a forward force acting on this. Now, something that we could say is maybe some like air resistance, but to make our lives easier, and like physicists often do, let's say it's in a vacuum. So no air. So are there any other forces acting on the football? And the answer is no. That the free body diagram of this projectile while it's in motion is exactly the same. It does not change as far as forces go. The only force that's acting on this object the entire time that it's flying through the air, neglecting air resistance, is gravity. And that's it. And so that's another kind of like base portion, like definition of a projectile, is really kind of what we see is projectiles have a force due to gravity. And if we're being really technical, then they might have air resistance, right? Force due to gravity and maybe air resistance. Okay, so if I look at a free body diagram and really I'm only seeing a force due to gravity and that's it, it's a projectile. It is flying through the air. Maybe it's falling towards the ground. It certainly is falling towards the ground either way, but that's in projectile motion. Well, what do we know? Like, we know Newton's second law. We know that the force is equal to mass times by acceleration. And we know that if we take force and we divide it by mass, that it will equal that acceleration. And so notice something. I'm going to call this time 0. Okay, 0 seconds. Let's call this 1 second, 2 seconds, 3 seconds, and 4 seconds. And let's say even 4 seconds was like moments before it hit the ground, right before it hit the ground. Okay. Notice that the force is exactly the same from 1, 2, 3, and 4 seconds. Like, the force has not changed. And the mass of the object from 1, 2, 3, 4 seconds has not changed. So if the force isn't changing and the mass is not changing, then the acceleration is not changing. That the acceleration is constant for all of them. So that's another thing that we can say is we have, and really I need to break this apart into the x and the y, but let's talk about the y direction. In the up and down towards the earth, away from the earth, y direction, so in the y direction, okay. So in the y direction, the acceleration is negative 9.8 meters per second squared. Because only gravity is acting on this. All right. Now, I'm saying that the acceleration in the y direction is 9.8 seconds because we actually have a force in the y direction, right? We actually have a force in the y direction, and that's causing an acceleration. Well, what about the x direction? Like, if we think about this for a second, as far as forces go in the x direction, right? Like, forces in the x direction divided by the mass equals acceleration. But however, the forces in the x direction are 0. There's no forces. There's 0 newtons worth of forces in the x direction. So yeah, we're going to divide it by the mass, and that equals acceleration, but 0 divided by anything is 0. Its acceleration in the x direction is 0 meters per second squared. Okay, now, reminder. When the acceleration is something other than 0, like 9.8, that is when something is speeding up or slowing down. So we are either speeding up in the y direction, or we're slowing down in the y direction. However, in the x direction, the acceleration is 0. Okay, the acceleration is 0. So when the acceleration is 0, it's one of two things. Either we are not moving in the x direction. Well, guess what? That's not true, because this is the x direction, and it's certainly traveling in the x direction, as well as traveling in the y direction. But it is 0 acceleration. So if it's two options are either it's not moving in the x direction, or it's moving at a constant velocity. When the acceleration is equal to 0, so the acceleration in the x direction is equal to 0 meters per second squared. This means that we have a constant velocity in the x direction. Okay, I know this is a lot, but let's look at this. Let's break it apart, because it helps when we break it apart. So turn the page. Here's what this diagram is showing us. We have a cannonball, and we shoot the cannonball off of like a hill, a cliff, and the cannonball's traveling here, 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 here. Okay? Now, there is a new image every second. So this is at 1 second. Let's write it right in there. So like 1 second. This one is 2 seconds, 3 seconds, 4 seconds, 5 seconds, and 6 seconds. What if I map this in the x direction? And what if I map this in the y direction? In the x and the y. So, and then of course here's 0 seconds. Okay, 0 seconds. So after 1 second, this is how far we've traveled in the x direction. Let's just look at x for a minute. After 2 seconds, this is how far we've traveled in the x direction. After 3 seconds, this is how far we've traveled in the x direction. After 4 seconds, this is how far we've traveled in the x direction. 5 seconds, and 6 seconds. All right. Really interesting. Notice the distance traveled in the x direction. Like, let's just say hypothetically to help us. And actually, we won't even do that. We're just going to call it like lowercase d for distance, like whatever distance that might be. Maybe it's 1 meter. Notice that it's exactly the same right here, and right here, and right here. So every second, it is traveling this exact same distance in the x. For every second, it travels a distance of d in the x direction. So what would, like if I were to draw velocity vectors, not acceleration vectors, not force vectors, velocity vectors. What would those look like in the x direction? So let's draw a velocity vector for each of these. Okay. So yes, it's traveling with some velocity when it leaves the cannon. And then after 1 second, guess what? When the acceleration is equal to 0, that means the velocity is constant. That means the velocity is constant. So in the x direction, the velocity stays the same. Let's do a little v sub x for velocity in the x. And we want these arrows to stay exactly the same size because the velocity is not getting bigger and the velocity is not getting smaller. It's staying the same because it's constant. Okay, now I do want to say this is in a vacuum. This is like neglecting air resistance. Okay? Now let's talk about the y direction. So here is how far we've traveled in the y direction after 1 second, after 2 seconds, 3 seconds, 4 seconds, 5 seconds, and 6 seconds. What's happening? Is the distance between these staying exactly the same? Distance was this much, and it became this much. Now it's here. Nope, certainly not staying the same. It is increasing. The distance is increasing as time is going by. If we cover a greater amount of distance in the same amount of time, that means that our velocity has increased. We have a higher velocity. So like if I were to draw a velocity vector for this, let's draw one here. Okay, ready? So I'm going to draw velocity vectors. The magnitude, the size of the arrow represents the size of the velocity. So at first, our velocity is really small. There's our velocity vector in the y direction, v sub y. And then it gets a little bit bigger, v sub y. And it gets a little bit bigger. And then a bit bigger. And even bigger. And even bigger. The velocity is increasing over time. And when something is speeding up or slowing down, that means that there's an acceleration, that the velocity is not constant. And the only force, like we learned before, the only force acting on this, if we're neglecting air resistance, is gravity. And when there's only gravity acting on something, that means it has an acceleration of 9.8 meters per second squared. Now we can put a little negative sign on here, meaning that it's going down if we want to do that. But whenever there's an acceleration, that means that we are either speeding up or slowing down. In this case, we were speeding up. All right. So this brings us, you guys are doing great. This brings us to our last concept, and then I'll have a video for you guys to watch, and then next time we're doing our project, which I'm excited about. So, it's a thought experiment. A bullet shot and a bullet dropped. Okay, so I know this is a little confusing, but here's the idea. Like, I got to draw two separate pictures to explain this. So, the first picture I'm going to draw is someone facing away from us. okay? And they have they have a gun and they're facing away from us, and then they have in their other hand, or a person next to them, however you want to say, they're holding a bullet, okay? So it's like one side is like an actual item that can I'm trying to think of the best way to say it, is an actual item with gunpowder that can eject a bullet at some velocity out of the barrel, and then they have another identical bullet that they are holding, okay? And so the idea is, what if, now I'm going to change the view, okay? So now I'm going to look at the side profile. So we have our person, okay, so they are going to fire the bullet at the same time as they drop a bullet. So imagine, like, we also have a bullet in their other hand. I should have drawn like over here. Their other hand, then they're holding a bullet at the exact same height. Another important part of this is that, do you see the angle? It's got to be like perfectly horizontal with the ground. Like the gun is not angled up and it's not angled down. It's like perfect horizontal. So here's the question. If they fire the gun and drop the bullet at the exact same time, which bullet will hit the ground first? Will it be the bullet that was fired, or will it be the one that was dropped, right? Because the bullet that's fired is going to have this kind of path to it, right? Something like that. And the bullet that's dropped is going to have a path to it that looks like this. And so if we fire the gun and we drop the bullet at the exact same time, which one is going to hit the ground first? Okay, pause for a moment, talk to your group, come up with a hypothesis. Which bullet is going to hit the ground first? And then when you guys are ready, hit play again on the video, and then we'll see how you did. So here's the idea. In the X direction, there's a difference here, right? Like, this bullet doesn't have any velocity in the X direction, where this bullet does have velocity in the X direction. However, the Y direction is identical for the two. That whether it was traveling here or it was dropped, same idea. This is how far it travels in 1 second. This is how far it travels in 2 seconds. Here's 3 seconds. Here's 4. Here's 5. Here's 6. That the one that was dropped will hit the ground at the exact same time as the bullet that was fired. Isn't that crazy? Isn't that amazing? Like, they travel so far, these cannonballs and these projectiles, they travel so far. But if we were to just drop one at the exact same height, then they would hit the ground at the same time. Okay, so everyone, thank you for taking the time to take these notes. We'll talk a little bit more when I get back, just like refresh your memory on this concept. And then we are going to dive into the project. And then for the remainder of class period today, I want you to watch this video, and then you have a worksheet that goes with this, and that's what you're going to be turning in. So make sure you turn in that worksheet before you leave today. All right. Thank you, guys. Thank you for your understanding for me not being there. And I will see you all on Tuesday.